Hello, I am going to discuss the inductor design in this video. First, we will derive the inductor design equations. We can use Ampere's law to derive the equations. Here we can see that if we multiply the magnetizing intensity with the length of the magnetic path, then this product will be equal to the current enclosed by this path. So the actual formula is this one. This is the Ampere's law, and if the flux is uniformly distributed in this core, then we can just multiply the magnetizing intensity with the length of the length of the flux path, and then this will be equal to the current enclosed by this path. And in this case, this is the total current enclosed is number of windings multiplied by the current. And if we divide this magnetic path into two parts, one is the path due to the core. This is this path from here to here, and then here mean path, and then into the other path is this air gap path. So if we uh, integrate the intensity on this path, we will get this expression. If we integrate the magnetic intensity over this path, we will get this expression. So if we put the value of the flux density instead of the magnetizing intensity, then we will get this equation, and by rearranging we will get the value of the magnetic flux density. So this is our first equation to get the value of the flux density. Now if we use the equation of the flux linkage, then we have this expression, and if we use the value of the phi as BA, area of the cross section of the core, and then use this value of I in this expression, then we will get something like this one, and after rearranging we can get the value of the inductance with this equation. In this equation, this part is called the AL part, so I have written it as AL. So we can find then the value of the AL with this expression, and if we put this value of AE on this direction, then we will get the ratio of AL and AE, and this ratio will be then can be used in the equation 1, which is this one. So we can use this value here, and if we replace this factor in equation 1 with this one, then we get the value of the flux density in this way. So now we have these equations. One equation for the flux density is this one. This is the equation for the inductance. And if we use this part, then we can get the number of turns from this equation. And if we use this AL and AE factor, then we can find this flux density from this equation or from this equation. So we can use these equations to find first the number of turns and then the flux density to see that if we are not exceeding the peak flux density which is allowed. So here I have shown an inductor design example with no air gap. So I've used current of 8 ampere peak, and this is my inductance, and this is the AL value of the core with no air gap, and I am using this type of core, and the material of the core is N87. So if we use the formulas which we have derived, we get 5 turns. And if we check the value, maximum value of the flux density, then we will get this value, and this is greater than zero point 0.2 Tesla. The value of the zero point 0.2 Tesla is selected on the basis of the temperature rise. So the core, that actually the core can is not saturated at perhaps will not be saturated. We have to check it, but this value is actually depending upon the temperature rise. So we want to keep the core flux in this range. So it is this way, as this value is very high, so we have to reduce this value with the help of the air gap. So as the core is saturated, so you must use air gap to reduce the saturation. Actually the core is saturated because this is very high, um, but this constraint of 2 Tesla is actually not due to the saturation, but it is due to the temperature rise. We want to keep the flux in this region, so we will use an air gap to reduce this value. So now we use an air gap of 0.5 millimeter, and now we have an AL value of this. And if we use this AL value for this inductance, we get 14 turns. And if we use the equation to find the maximum flux density with 8 ampere and 14 number of turns, we will, and this with this cross section area, we get this value. So now this value is close to this one, but it is still not but it is still greater than this one. If we want to further reduce it, we can increase the air gap, and this we will do in the next example. Here I am using an air gap of 1.5 millimeter. Here you can see the AL value is this one. If we use this AL value, we get 22 turns. And if we now calculate the value of the maximum flux density, we find 0.198, which is less than zero point 0.2 Tesla. So we are now safe. So now we can use these 22 turns with this air gap on this N87 core. So our design is complete. We have the number of turns, we have the core, we have the air gap. So the design is complete for the number of turns. Now we have to find the inductor size, the size of the wire. So to find the size of the wire, we have to find this we have to use a current density value of 4.5 amperes per millimeter square. This is the standard value. This value can be in this range. I'm using this value, and if we have a current of 8 ampere RMS, then we can find the cross section area of the wire. So if we plug the values, we get this cross section area. So our wire will have a cross section area of 1.77. If our operating frequency is high, for example 400 kilohertz, then we have to consider the skin effect. So we will find the skin depth with this formula for this frequency and for the copper, and we get this value. So we now can have a radius of the wire equal to this value, or the diameter equal to twice this value. So now we have to use many wires of this radius to get this area. So the area of this wire is calculated here. So we have one wire with this cross-sectional area, but we need a cross-sectional area of this one. So we will use this formula to get the number of wires which we need. So we will need 54 litz wire to make one wire of this cross-sectional area. So now if we go to this producer of the wire, we see that it has a wire which has 60 litz wire with this diameter, and it has a cross section area of total cross section area of 1.88. So we can now we can use so I have given this data here. The diameter of the wire is this one, the number of litz wire are 60, and the cross sectional area is this one, this value, and with the required cross section area is this one as calculated here. So we can use this wire for our application. So here I've shown the data sheet of this TDK core. Here you can see the value of the cross-sectional area which I used, and this is the length which can be used to find the AL value. And here some AL value, here there is the AL value is shown for an 87 wire without air gap, and here The AL values are shown for different air gaps. We use 1 millimeter air gap, we use 1.5 millimeter air gap, and 0.5 millimeter air gap, and these were the values which were used. So here you can see that the value is zero point 0.2 Tesla for a frequency of 100 kilohertz with a temperature rise of 100 degrees centigrade. So we can, if the but we are using a frequency of 400 kilohertz, so our temperature will be higher if we have a continuous operation. But if for the applications for which the inductor is not continuously running, it is running with a particular duty cycle, then we can also use, for example, this value for 400 kilohertz if the operation is not continuous, as in our case. We are not, for our application, we are not activating the switching power supply continuously, so we use this value at 400 kilohertz to design our inductors. But if the operation is continuous, then we can use the other equation, something like this one. Here you can see that for different frequencies, different cores are given, and these are the performance curve. Here you can see for the temperature rise of 100 degrees centigrade and a power loss of 300 kilowatt per meter square. These curves are drawn, and from these are the performance factor versus frequency curves, and we can use here any core depending upon our frequency. For example, if we have a 400 kilohertz frequency, then we can choose a core in this region. And here we can see if we have N87 core, then our value of this product frequency and flux density product will be in this area. And if we substitute the value of the frequency, then we will get the maximum value of flux density allowed for this core for a temperature rise of 100 degrees centigrade. So we can use these curves to select the cores. So we usually choose a core which has the highest value of this product. But as the N87 cores are easily available, so we can also use this core for our 400 kilohertz frequency, because this product is not very different from the other cores. So now we go to the next slide. Here I have shown how to calculate the area product for inductor design. Here is the bobbin shown, and here we can see that this is the area where we can bind our winding. So this area is equal to 7.3 multiplied by 26. So this is the width of the area, and this is the length of this area. So our winding area is 189 millimeter square, and the cross-sectional area of the core is this one, which we can see on this slide here. And now the area product will be equal to this value. So this core on this particular bobbin and core have area product of this one. So our area product will be less than this value if we want to use this bobbin and the core. So we now derive the equations to calculate the area product. So if we have this equation of the flux linkage equation, if we substitute this phi with the flux density, then we get this value. And now if we use the other equation of the window area, then we have this equation. So this equation is actually number of turns multiplied by the cross section area of the conductor. So this area is the area which will be used by the copper of the windings, and this is the total winding area, and this area will be a fraction of this total area, and this number is usually 0.4. So our total winding area will be zero point 0.4 of the total window area. So from here we can calculate the number of turns, and with if we use this value of n in the above equation here, then we can get this expression. And in this expression, if we use this expression for the cross-sectional area of the winding in this equation here, then we get the area product. This is the window area multiplied by the cross-sectional area. So this product here, this product will be equal to this value. And with this value, and by using all these values, we can now find out the area product which we require, and which require this area, this value of the area product, as this value is less than this value calculated on the previous page, this one. So this means that this we can use this core for our design. This is usually the first step which is done when we want to select a particular core and a bobbin for any application. So here I have shown the calculation of the AL, which is shown on the slides. This AL value can be calculated uh, with the help of the core size. So I have shown this here, how to calculate. This is the formula to calculate the AL value. This is the cross-sectional area of the core. This is the magnetic length, core length, mean core length, and this is the air gap length, and these are the permeabilities. So if we plug all the values from the data sheet, this is the air gap length, this is the total magnetic length, and we get the value of 213 nanohenry per turn square. So this value is actually not the actual value of the AL, because the air gap area will not be this, it will be a little bit bigger due to the fringing. So we have to calculate a fringing factor. This can be calculated with this factor, with this equation, and if we plug all the values of the air gap and the cross-sectional area and the winding length, we get a factor of 1.29. So we have to multiply this 1.29 with this value to incorporate the effect of the fringing. Then we will get a value of 276. So for the air gap of 1 millimeter, we get an AL value of 276. And if now we go to the data sheet, we see that for 1 millimeter it is 272. So it is approximately the same value. Similarly, you can calculate all other values with this formula. So now I am going to discuss some practical things while winding the inductor. So there are some we have to keep. The first point is that we have to keep the air gap as small as possible, as this will reduce the fringing force. For example, if this air gap is very small, then this fringing here will be small, and when this fringing is small, usually there will be no core losses, and there will be less eddy currents in the winding also. So this fringing, this flux will induce eddy currents in the winding, and these windings will also become hot due to this flux. So we have to keep this air gap length as small as possible. So if divide the total air gap in different legs, if larger air gap is required, so if we require larger air gap, then we can divide this air gap into different legs. And for example, we can also make an air gap here, and an air gap here, and also here. So we can divide the total air gap in 3 legs, or in this case in 2 legs. So this will reduce the fringing flux. The fringing flux causes more core losses due to eddy currents induced in the direction of the laminations. So this we can see here. So this is the fringing flux. So this flux will induce these eddy currents. On these eddy currents mm, are not crossing this, are not perpendicular to this laminate to these laminations. So they will not be obstructed, and this will cause a temperature rise in the core. So this is another point. So now keep the ratio of the winding area and the cross section area as small as possible. This means that the ratio of this area and this cross sectional area must be small, because if it is small, then we will require lesser windings, and the lesser windings will then require a smaller air gap. So while choosing a core, we have to consider this effect that this area must be small and this area, cross-sectional area, must be large. So this will also then produce a smaller air gap. The other point is keep the number of layers of winding as less as possible. So here we have 3 layers. Usually it is good that we only have 2 layers, because the outer layers will have induced current due to the inner layers, and this effect is called the proximity effect. So there will be extra current flowing in these outer layers uh, due to the induction phenomena from the inner layers, and this will cause um, hitting of the outer layers. So to avoid the proximity effect, it is best to use 1 layer, but one can use up to 2 layers if the frequency is high and the skin effect is not good. So you can use 3 layers also, but if the frequency is low and the skin effect is not affecting too much. So now this is another slide which I already have shown. Here is another point that if we are when we are winding the wires, we have to keep away from these edges, because this flux will also induce eddy currents in the windings, and the windings will become hot due to the eddy currents. It can also be seen here that these edges are causing eddy current are causing eddy current at this point, because they are entering at the right angle to the laminations, which are usually in this direction. So this flux will also induce eddy currents in the core and also in the winding. So we can wind perhaps in this region here, uh, but we have to avoid these edges. So here I have written avoid winding near the edges. It will increase loss in the windings if we are not winding, if we are winding in this region. So this is all for the inductor design. Thank you.